Braxton is with us.
A smile comes on his face, tears rush to his face. Probably thought he was going to get what he used to get.
Let's see who else is with us. Oh, we've got a good crowd. We have Ashley, Alex, Ben Seaman, Ben Harris, Samuel, Julian, Darren, and Brendan, Braxton. Got a wonderful class. And let's check the time. Oh, it is time for class. Time snuck up on us. Let's see, you have a homework that's due Sunday. Today's Thursday. Let me look and see the schedule here. Yeah, you got a test that will be available next Tuesday. So you need to start studying for that maybe next Monday night. Okay. Well, one of the topics today I wanted to cover was shear flow. Let me write that down. No, I don't want to do your homework. Let me see. Let me see what would be good to give you guys. Where is this stuff about shear flow? I think it's chapter 7. And let me snoop around here. Yeah, there it is. Shear flow. It's on page 386. Yeah, I want to talk about that. But let's see what would be a good problem to give you. Yeah, there's one there. That would be good. All right. But before we launch into the exciting world of shear flow, do you have any questions for me? Well, I wonder if I'm even connected. Let me go ahead, somebody. Hello, say hello.
Hello.
Yeah, hello. Yeah, we're connected. Yeah, we're doing okay. Well, let's see if I can explain this shear flow stuff. And then we'll work a problem. Does that sound good? You're supposed to say, oh, yes, it does, Mr. Griffin. Okay, well,
That sounds good.
yeah, it sounds good. All right. I've told you guys that if you have, they're talking about built-up members, and sometimes they'll put layers of maybe 2x6s together, and they can they can glue them even. You can glue a whole bunch of, well, maybe 4x6s, and you can make a beam out of that. See, if you glue them. But there's a weakness there where they're glued and they can slide if there's enough bending stress. You guys know that when you bend something, it creates not only normal stress but shear stress. See, the normal stress is given by this equation, and the shear stress these are caused by bending. And see, if you bend this thing, usually the beams that we're talking about, they kind of sag in the middle. So there's a force from this top, whatever it is, of 2x6, on the bottom 2x6. There's a shear force going to the left. Here, I'll just draw us a little piece of that. Here we go. There's a shear force going to the left on that. And that shear force comes from the top piece. That makes sense, because the top piece wants to slide if this thing is being bent. And that shear, they have a thing called shear flow, and what it is, here, let me write that for you. They use a symbol W for it. It's called shear flow. No, they use a symbol Q for it. It's called shear flow. And what it is the shear force divided by the length. See, there'll be a force on that. There'll be a force on that bottom board going to the left, and the length is whatever the length you want to talk about. Usually they'll nail it. Maybe they'll put some nails in here. See, every so often they'll put some nails in there, and the length is the distance between the nails. The shear flow is, this is the symbol for it, it's Q, and it's equal to that force. It's like a shear force, only your shear force on your beam is a force going down like that. But see, if you looked at a little element inside the beam, a little stress element, you've got shear stress doing this. See, if you got shear going down on a left, on this face here, if that's going down, you got to have something going up. Some of the forces have to be equal, and that would cause rotation. So you have to have shear stress going this way here on your little element. I don't know if that made a lick of sense, but let's continue this equation here. Now that force is equal to your shear stress times your area. You guys all know that. Stress is equal to force divided by area. So force is equal to stress times area. Okay. And we've got a lovely equation for shear stress. It's right here in that area that we're talking about. I'll try to draw it for you. It's kind of an area in here like this, where this is the thickness of your beam, and this is the area that we're talking about is this area here. Why don't we just call that, what are we going to call that? Maybe X or L? Let's call it L, I guess. So what you have here is VQ over IT times TL. Right? Just a minute. I just about got this figured out. VQ over IT Guys, I'm having a little trouble here. Just a minute. Having a teeny tiny bit of trouble here to show you where this equation comes from. That is shear flow. It's the force per length. And that is the length. Yeah. And I forgot my length. There's my problem right there. Okay. So there, I've got the area, which is TL. I've got an L down here. There we go. Okay. So when you do that, by Jove, couldn't figure out what I was doing wrong there. I forgot to divide by my length. Because see, shear flow is force per length. Look at here. The T's cancel, the L's cancel, and you get VQ over, make some room here. VQ over I. By Jove, we're done. Now look at that equation on page 386. That's where it comes from. I didn't explain that very good, but see, there's a force on that bottom board that you're trying to fasten to the top board. It's going to the left, and shear flow is that force. Maybe I could draw it better like this. Here we go. Let me get some red here. There's a force on that bottom board going to the left. If this thing is being under a bending load, and that force is equal to the shear stress times the area. Well, the area of that is equal to the thickness of your board times whatever length it is. Okay. So we got tau A over L, but tau is VQ over IT, the shear formula that we developed in learning how to use. And so you take the area, which is TL, and divide by L, and by Jove, you get that. That's it, guys. We just came up with a formula for shear flow. All right, let's see if we can use it here. I thought we could go through one of these problems. Now, this problem is going to take a while. But before I do, are there any questions or comments? Well, go ahead.
After you do that problem, whatever problem we're gonna do, I just want you to go over 7-5 a little bit.
Let me find 7-5. Just a minute. You know what page it's on?
Yeah, it's on page 382.
Thank you so much.
I'm just having trouble with the moment of inertia with that
Oh, okay.
wide flange beam.
Yeah. Well, here, I'll write it out for you, Mohammed. I just need some room to do that with. Now that's part of your homework there, Mohammed, that you know that. And
Yes.
he's having a little trouble getting the moment of inertia. And if I show you how to get the moment of inertia, I bet you can finish the problem, can't you?
Yes.
I bet you can. Well, now you're really lucky here, Mohammed, because it's symmetrical. It's symmetrical. And you can use that shortcut method that I taught you guys. I don't know if I have this to scale very good. Not too bad. The easy way to get this one is to take this whole thing which is pretty easy to do. If you take the moment of inertia of that whole thing, it's 1/12 the base, and they said the base is 0.3 times the height. Now the height is going to be 0.44. Are you with me so far?
Yes, sir.
Was that a yes?
Yes.
Yeah, okay. But see, then you have to subtract these green areas. I don't know if green shows up on your computer there. But see, what we're going to do is we're going to subtract these green areas because they're not there. We're going to subtract them. All right, here goes. Minus, well, you could just consider this something that has a width of, well, it'd be 0.3 minus your 20, so that'd be 0.28 times the height of that, which is 0.4 cubed. Now that's doing it the easy way. Let's go ahead and do that. I'm plugging that in now, Mohammed. I'm getting 6.36 blah, 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 blah times 10 to the minus fourth meters to the fourth. Did you get that?
Yes, sir.
Yeah.
How you get that 0.28? Can you show me? The minus 112 in 0.28?
How do I get the 28?
Yeah, yeah.
Well, see, from here to here, it's 0.3. And this right here is 0.02. So what you do is you take 0.3 and you subtract 0.02 and you get 0.28. Or you could do it this way. This is 0.14 and this is 0.14. They add up to 0.28. And you could break this into two pieces. Instead of writing it like this, you could go 0.14. Here, we'll do it that way. Minus 112, 0.14, 0.4 cubed. I was just too lazy to write that out, and I wrote it as 0.28. Does that make sense?
Yes, it does.
And so you're okay now?
Yes, sir. I'm okay. Thank you so much.
Okay. All right. Well, I want to do another problem that's going to be a little harder than that. And that's problem 735. Yeah, here it is. Now, to do this properly, you really need an accurate diagram. So I'm going to attempt to do that. Now this one has 12 inches. I think I'm going to use 12 centimeters. And I'm doing 735, and I'm trying to draw it to scale. I really would like to have it bigger than that. I think I'm going to use inches instead. But I'll use a scale. Instead of 12 inches, I'll use 6 inches. There we go. That's 6 inches. And the width there is 1 inch. So that'd be a ½ inch, wouldn't it? Yeah, that'd be a ½ inch. So let me draw that. Here we go. I'm doing this to scale. This is what you're supposed to do. Right, I did that to scale. And then these here are 10 inches, so that would be 5 inches. I'm using a scale. And these are 1½ so that'd be 3/4. That puts me right there. Yeah, I'll just fake it. There we go. Then we'll do this one down here. Now we can label all that stuff. This is 12 inches. Come on now. That one's 12 inches. These are 1.5 inches. These are 5 inches. No. They're 10 inches. They're 5 inches on my scale. See, I just divided everything in half, but we're putting the correct amounts in there. And then, now here's where I goofed up. This is where I goofed up. This is only 3 inches. Put you right here. There we go. Yeah, there we go. These are 3 inches, 1.5 inches. The 12 inches here, 1.5 inches. 10 inches. I think I got it pretty good. Okay. Now our first task is to get the moment of inertia. Well, you know that method we just used on Mohammed's problem, where we had some stuff and we subtracted some stuff? You can't do that on this. Only if it's symmetrical about the X and Y axis can you do that. Here we've got to do this one the old-fashioned way. So here we go. Now to do that, first we got to find the centroid. Well, let's measure everything from here. We'll measure our distances down here from the bottom. And to do that, you need to get your red pencil and put a red dot right here, here, and here. And we need those distances. Well, this distance here, you know what that is? That's 0.75 inches. it's half of 1.5 inches. And you see this distance here? That would be 7.5 inches. Do I need to explain why it's 7.5 inches from the bottom to that red dot? You okay with it? And finally, I need this red dot here. See, this is 7.5 inches. But if you want to go to this red dot up here, that's going to be 12 inches plus 1.5. What does that make? 13.5 plus 3/4. 14.25. I wonder if I did that right. Let me do that on my calculator. From the bottom, I'm trying to go from the bottom here. All the way from the bottom up to that red dot is the 1.5 plus the 12 plus the 3/4. Yeah, 14.25. Did that right. We have to find all those in order to find the centroid.
Mr. Griffin?
Yes, I'm listening.
I think at the bottom of the beam, did you write 3 at the bottom of the beam? The 3-inch?
It's wrong. It's 6 inches.
Yeah, it's 6-inch. Yeah.
Mohammed had just gotten the first thank you point of the day, and I appreciate it very much. It's actually 3 inches on my ruler, on my scale that I used, guys. But I divided the 12 inches by 6 inches. You understand? And then the 10 inches, I made 5 inches. But Mohammed was absolutely right, and I appreciate it. Okay, and I think we did all that, and now we're going to write the centroid. Before we can find the moment of inertia, we've got to get this centroid. And I tell you what it's going to be. There's a formula. They all look the same. They go like this. All these centroidal formulas look the same. So I'm just going to do it. Here goes. It's going to be 0.75 times this area. What that is 6 times 1.5 plus 7.5 times this area. Now they said that the thickness of this one is just 1 inch. Remember, I used 1/2 inch, I think, on my, yeah, see, I used 1/2 inch. But that's just 1 inch wide there. So you go 7.5 times 1 inch times 12 inches plus 14.25 times 1.5 times 10 inches. Then you have to divide by the total area, which is 6 times 1.5 plus 1 times 12 plus 1.5 times 10. And we'll have our centroid. Now go ahead and do that. You do it, and I'm going to do it, and we're going to get our centroid. Well, I got my centroid and I got 8.625 inches. Now, if you got that, say, uh-huh.
Yep.
There's one.
That's what I got.
Yay, there's two. I need another uh-huh. I need another uh-huh.
Yep, I got the same.
Yay, we've got the centroid. Now let me draw that. 8.625. Well, on my scale, that would be 4.3125, right? Yeah, it puts you right about right in here. That's where the centroid is. Here, I'll draw up here. I'll go up here. What's that 14.25? I got lost. Oh, that's that distance all the way up to the top. But the centroid is 8.625. It kind of makes sense that it's not going to be where that red dot is, because this flange is bigger than that flange, and so the centroid kind of moved up a tad. Kind of makes sense. Now, to find the moment of inertia, we're going to need these distances here. You see this distance? That's 1 inch. We already know that. I'll put 1 inch right there. There we go. You see this distance here? I need that distance. I'll tell you what it is. It's 14.25 minus 8.625. Here, I'll write it for you. I need that distance in order to find the centroid. Okay, well, let me do that. Let's see. I need to subtract. I need to add 14.25. This distance right here is 5.625 inches. I need this little bitty distance right here. See it? See that little teeny tiny distance? I tell you what that is. That's 8.625 minus 7.5. Let me see what that is. I'm getting 1.125. That little itty bitty distance is 1.125. And finally, I need this distance here. Now, wait a minute. I'm getting mixed up. I don't want that distance. No, 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 no. I want the distance from this centroid to there. That's what I want. Now, I'll tell you what that is. That's 8.625 minus 0.75. Let me see what that is. 8.625 minus 0.75. I'm getting 7.875. The distance from this centroid of the whole piece to the centroid of this bottom flange is 7.875 inches. Now we're ready to get the moment of inertia. Now I know this is very tedious, time-consuming, and no fun. But isn't a lot of things that we have to do like that? I don't know if you have kids, but changing diapers is kind of tedious, takes time, and it's really no fun. You might enjoy it, I don't know it. Maybe it's fun for you. But there's just a lot of things in life. You have to take the trash out. You have to wash the dishes. You got to take the car in to get it serviced. But life, you got to pay income tax. There's just a lot of things that are kind of unpleasant and tedious, and you wish you didn't have to do them. But it's important. We've got to get this moment of inertia for several reasons. The shear flow depends on it. See, this is a built-up thing. They've taken this flange and they've attached it to this web, probably with nails or glue or bolts or something. Looks to me like they've used some kind of dowels there. Maybe they've drilled holes and put dowels in. By the way, if you wondered what we're doing, we're doing problem 735. And now we're going to find the moment of inertia. I just need a little room here. I don't need any of this stuff because we figured it all out. One of the things they're asking in this problem is what the maximum shear is. We'll find out. We got an equation for it. No. They're giving us the maximum shear. They want this. They're giving us the maximum shear that can be allowed for this material. And we're going to get all of these things. And they want us to find the maximum shear. They're giving us the maximum shear stress. We're going to find all of these things, and we're well on our way. This maximum shear stress is going to occur right there. Haven't I told you that the maximum shear stress occurs at the centroid? That's where you get it. That's where you get the maximum shear stress. But in order to find this unknown, see, we're going to get all these. To find that maximum shear that this you can allow in this particular beam cross-section, we must get the moment of inertia. Okay, well, here goes. Now you got to do this the old-fashioned way. Remember that method I used on Mohammed's problem where we subtracted some stuff? You can't use that. That won't work unless you have a very symmetrical beam cross-section. So here's what we're going to do. We'll do it one piece at a time. We'll take this bottom piece. That'll be 1/12, 6 times 1.5 cubed. But see, that would be the moment of inertia of this bottom flange if it was figured about its centroid. Well, it's not. We've got to add to it the parallel axis theorem. We'll take this area, which is 1.5 times 6. Times 7.875 squared. That's the parallel axis theorem. See, this is the moment of inertia about the centroid of that bottom flange, but we're trying to find the moment of inertia about the centroid of the whole piece. And you have to take that area times the distance from the centroid of the whole piece to the centroid of the bottom flange. There it is. Okay, we're not done yet. We have to do the web now. Now the web's going to be 1/12, 1 inch times 12 inches cubed. Didn't they say it's 12 inches? Yeah, that's right. But see, that would be the centroid of the web about its center. Well, we're trying to find the centroid or the moment of inertia about the centroid of the whole piece. So you have to go 1 inch times 12 inches times 1.125 squared. And finally, we've got to do this top flange. Okay, well, that's going to be 1/12 times 10 inches, 1.5 cubed, plus the area of it, which is 10 times 1.5 times that distance there, the distance from the centroid of the whole cross section to the centroid of the top flange. It's 5.625 squared. All right, I want you to add all those up and tell me what you get. I'm going to do it. You do it and tell me what you get. It's tedious, a little bit boring, but it's not that bad. Try filling out an income tax sometime if you want to try something tedious and boring. Well, here's what I got. Now what would be the units on that? I'll ask somebody. Ashley, you've always helped me in the past. First of all, Ashley, how many courses are you taking with me?
2.
2?
Yes. This in dynamics.
Well, bless your heart. Ashley, what do I put in here for the units on this moment of inertia?
Inches to the 4th.
That's correct. Good going. Now, anybody out there, if you got 1196.4375, say, uh-huh.
Uh-huh.
Hey, I got 2 people already. Anybody else?
Yep.
I heard a yep. Hey, looky here, guys. They're going to give us this. They said that is, I'm reading it here. I'm on page 392. We are doing problem 735. It's on page 392. And they said that this is 400 PSI. Does that show up on the board? Yeah, that shows up pretty good. 400 PSI, yeah. And hey, look at here. We just got this. We're making progress. We got 2 out of these things. Now the thickness, they're talking about the thickness of this web where we're trying to figure where the maximum shear stress is. Well, it's 1 inch. I know what that is here. I'll write it down for you. T is equal to 1 inch. That's how thick that web is. They said it's 1 inch. So look, we got that. You know what? We got that, and that. If we could only figure out this Q thing here, we could figure out what they want, the maximum shear that this beam is allowed to have. Okay. Well, let's figure that. They have a name for that. They call it the first moment of area. But I need some room to do it. So I'm going to erase all this if that's okay with you guys. If it's not, you could always watch the YouTube video. It'll be on there. My IT person will put it on there. Let me erase all that. I need the room. Several of you got it. Oops, I just erased it. Oh well, I've got it written down. We're going to try to find this Q thing. Now, by definition, that's what it is. It's the first moment of area is the name of it. It's the first moment of area. I told you about it last time. You've seen it before in some formula. I know you've seen the second moment of area. It goes like this. That's called the second moment of area. And that happens to equal the moment of inertia. That it's the definition. Well, this is the definition of the first moment of area. But here's how you do it. There's a step-by-step process. Step number 1, step number 2, I don't know, maybe step number 3. The first step is you draw a line through. Let me make a green line. That'd be good. I'll get some green color here. You just draw a line through. There's my green line. You draw a line through whatever place that it is that you want to find the shear stress. You're trying to find the shear stress. See, we're trying to find the shear stress. We know it's maximum there at the centroid. And to find this first moment of area, you draw a line through that place, the centroid, where we're trying to find the maximum shear stress. Step number 1, you draw a line. Da-da-da-da, we did that. Step number 2, you color everything above the line. Okay, well, let me do that. I'm going to color, that's above the line. You know what? This is above the line too, isn't it? Color everything above the line. And then step number 3, you just add them up. You add up all the YIs and AIs. Because that's, we don't need to integrate anything. We just have rectangles. We don't need to integrate. We know how to find the area of a rectangle. Okay, here goes. We're going to do it now. But to do it, we've got to find this distance here for that first area. Now that first area, I don't even know how long it is. I know it's 5.625 from here up to here, but you know what? That there is 3/4 of an inch shorter, isn't it? So let me write that down. This is ugly, but we can do it. I think that green area right there is 5.625 minus 0.75. Here, I'll write it out for you. 5.625 minus 0.75 is 4.875. So the area is 4.875. Well, from here up to half of it would be half of that. So it would be 4.875 divided by 2. That'll get you this little distance here, times 4.875 inches times 1 inch. That's the area of it. But we're not done yet. We got to do this top flange. So we have to add. Now we already have this distance here. Isn't that nice? The 5.625. I've already got that. 5.625. And the area of that one is 10 inches times 1.5 inches. That's it, guys. You're looking at it. That's the first moment of area. Okay, do it. Do it and tell me what you get. I got a Q of 96.25. That's enough. Now, if you got that, I'll wait a minute. But when you get that, I want to hear an uh-huh.
That's what I got.
Yay, there's 2 of us.
Yeah, I got that.
There's 3 of us. I need a couple more uh-huhs. Yeah, there's one.
Mr. Griffin,
Yes.
can you explain this equation one more time?
Yeah, what we're doing is we're summing all of the distances from the centroid of the whole cross-section to our areas. There's 2 areas here. Now this area here is 4.875 times 1 inch. And the distance from here to the middle of that area is 4.875 divided by 2. Now we're going to add this top flange. Now that area is 10 inches times 1.5 inches. That's the area. The distance from here up to that red dot is 5.625. This is how you calculate this first moment of area. This is the definition, but we don't need to integrate. We're just going to add up those 2. I don't know, Mohammed.
Right.
You think you're
I'm just
okay?
confused. Yeah, I'm just confused how you get the 4.875.
Oh,
Like
okay.
how-
Here, let me show you where I got that from. I know the distance from, I never wrote it down, Mohammed, but the distance from the bottom up to here, I'll sneak it in right here. From the very bottom up to here, that distance is 13.5 inches, I believe. Because you got 1.5 inches, you got 12 inches, yeah. And then I'm going to subtract the 8.625, and that should give me this distance from here to here. Let me see what you get. So 5, 7, that's where the 4.875 comes from. Do you see it?
Yeah.
Okay. And half of that, well, you divide by 2. 4.875 divided by 2, that'll give you this half distance, which you have to have in your equation here.
Oh, okay. Now I got it.
All right. Okay, now look here, guys. We know what this is. It's 400 psi. We know what the Q is. It's da 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 da. There it is. We know what the I is. Well, I erased it, but here, I'll put it back on the board. And you guys agreed with me. I heard several uh-huhs. It's 1196. .4375 inches to the fourth. So we've got the I. Now the thickness is 1 inch. The Q is 96 point blah, blah, blah. We got everything except this V, and that's what they want. We're going to get that V now. And I'm going to shut up. Guys, here's an equation. We know everything except this unknown shear force. Solve it. I'm going to solve it, and we'll see what we get. Go for it. Maybe I should write it out. I did all that, and I got the shear. This is the maximum shear that you'd want, because with that shear, you'll get 400 PSI. And they said, we don't want to exceed that. But I got a shear of 4971.8 pounds. Did anybody get a shear of 4971.8 pounds?
Yep.
Yeah, there's two of us. Yeah,
Yeah.
there's four of us. Or three of us. I can't count that high. Well, great. Let's look and see how we did. This was problem 375. We're not done yet, but let's see if we got that right. This is problem 735. And they said the shear is 4.97 kips. The book says 4.79 kips. Now, what do we say? Well, you know what? That's the same thing. Oh, wait a minute. I read that wrong. 735. No, it's 4.97. Got a little touch of dyslexia going on there. The book says 4.97 kips. We said 4.971.8 kips. Same thing. They just rounded off. Hey, we're doing great, aren't we? We're doing just great, but we're not done yet. If you read the problem, they want to know something about the maximum spacing of the nails. If each nail can resist a force of 400 pounds. See, what they're going to do is they're going to nail this thing. Here, you know, it's a beam, and I guess it's a wooden beam, huh? It's a wooden beam. Our artist's rendition of the wooden beam there, and what they're going to do is they're going to pound some nails in here. Pounding it to try to keep this beam together. Okay. And this distance here, we'll call it L. We have a thing called the shear flow. I showed you where it came from. The symbol the book uses is Q. And it's the force that each nail can supply. And they give us that. They said each nail Doesn't shear off until you got 400 pounds of shear on it. So they're giving you that. And we have a formula for the shear flow. This thing here is called shear flow. That's the topic for right now that we're studying. It's called shear flow. And what it is that in this case, it would be pounds per inch. And they're going to give us this. And we have a formula for shear flow. It goes like this. That's the formula. I derived that formula for you at the beginning of our class. And the thing is, see, we've figured out this V. Let me circle that. There it is. It's 4971.8 pounds. And we figured out the first moment of area. Look, there it is. It's 96 point blah, blah, blah inches cubed. And look at here. We figured out the area moment of inertia. Blah, 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 blah. There it is. We got that. Look, here's an equation with only one unknown. And that's the spacing between these nails. That's what they want us to find. They want us the maximum allowable spacing. You could have them a little closer, but this will give us, you've got to have them at least this close apart. Look, here's a nice equation. All we got to do is plug in the numbers now. And they give us the F. Here, let me make some room here and I'll write out the numbers for you. They said F is 400 pounds. If you read the problem, it's on page 392. So they said 400 pounds. This spacing between the nails we'll call L. And we don't know what that is. But the shear we know, it's 4971.8 pounds. And the Q we know, it's 96 point blah, blah. Inches cubed. That kind of got erased there, but that's inches cubed. And then the moment of inertia is 1196 point blah, blah. Inches to the fourth. And boy, Jove. All we got to do is plug in all this stuff and get our distance between the nails. Go ahead. You do it. I'm going to do it. And we'll see what we come up with. Go for it. Now wait a minute. Just a minute. I might have done something wrong here. No. No, I think I did okay. I think I did okay. Yeah, I did okay. Plug all that in and let's see what happens. Here goes. I'm getting a really weird answer. I think I did something wrong. Yeah, guys, I think I made a mistake here. Yeah, I think I made a mistake. Let's see if I can fix it. I got a bad feeling I made a mistake. But where did I make my mistake? I got a feeling I made a mistake. But where did I make my mistake? Uh, okay. All right. I think this equation's okay. The I is okay. The V is okay. It's this Q. This Q is my problem. And see, here's my problem. What we're figuring out, I made a mistake. What we're figuring out is if this thing was going to have a sliding going on right there, but it's not. The sliding is right here. If there's any, this is where I needed to draw my line. Remember I gave you the little sermonette about putting a line through there and then coloring the stuff above the line. You don't color this. The stuff above, that's where that top piece is going to try to slide because of the shear stress. And so my Q is wrong. We've got to find the Q if this is where we're trying to find where they're going to slide. Okay, well, this Q is wrong. So we're going to do the Q over again. This Q is wrong. Do you understand? These are three different boards. And they're either going to glue them or nail them or somehow attach them. If it was metal, they could weld them. They could do welding. And see, the trouble might arise because of the shear stress. This top flange will want to shear on the web. And the Q, the little method I told you is fine. You draw a line where you're interested in finding this Q, and then you take your distance, but the distance is from here to here. It's 5.625, and the area is 1.5 inches times 10 inches, and that's it. Well, let's do that. Here goes. 5.625 times 15. I'm getting 84.375. That's what goes in right here. See that Q? If you're doing it there, and that's where they're going to slide, it's 84.375 inches cubed. Okay. I'm sorry I made a mistake, but I think we're okay now. Now plug that. You're going to have to solve this for the spacing between your nails. Go ahead and plug that in. Find that spacing between your nails now. Go for it.
Wouldn't you have to get a new shear stress? Or shear force, not stress.
This shear force is the shear force that's acting through the centroid here.
Okay, so that's the same.
It's the same. Yeah. It's the same. Well, I got an answer. Did you get a distance between the nails up here on the top of 1.14 inches? And if you did, say, uh-huh.
I did.
Well, there's two of us. Now let's see what they said. This was problem 735. Boy, Jove, that's what the book says. They said those nails have to be 1.14 inches at least. They can be closer, but they got to be at least that much. But now they have two answers. They have another spacing at the bottom of 1.69 inches. Well, let's see what that's all about. See this bottom flange? They're going to have to put nails on it too. Now, the force of each nail is still 400 pounds before it shears off, so that doesn't change. The shear, like my student I just talked to, the shear on the whole piece, the shear force on the whole cross-section that doesn't change. The moment of inertia of the cross-section doesn't change. What's going to change here at the bottom is that Q. We're going to have a different first moment of area. Now, here's how you do it. Here's the rules. See, this bottom flange is wanting to slide on the web, right? It's got bending stress on it. Shear stress on it. And the shear will cause it to slide if you don't have it glued or nailed or whatever. And here's the rule. Right here is where it's going to slide. So you draw a line through there. There we go. We're going to draw a line through there. And then to find the Q, we're going to have to, the Q is going to equal to the area of this, what is it, 1.5 times 6? That's 9 square inches, isn't it? Times this distance here. You have to go always from the centroid of the whole piece down to here. We already have that distance. It's 7.875 inches. So now we're going to get the Q, the first moment of area of that bottom flange. Here goes. I'm going to do it. 7.875 times 9. I'm getting this Q. Does this show up here? Yeah, barely. It's equal to 70.875 inches cubed. Here, let me write it all out for you. We've got a different Q now, and there'll be the spacing will be different on the nails on the bottom flange. Do I have enough room here? Maybe. The shear is 4971.8. This new Q on the bottom flange is 70.875 inches cubed. We know it's inches cubed. The I is 1196.4375. And this F here is 400. That's 400. So here's our new numbers. We're going to solve for this, what they call it L with a little b there for at the bottom. See this equation here now? I want you to solve. We know everything. If you can read my writing, that's an F. And it's 400 pounds. Solve for that distance between the nails on the bottom flange. And I'm going to do it. I want you to do it. Here goes. Well, I got an answer. Did you get the spacing between the nails on the bottom flange? I got 1.358 inches between the nails on the bottom flange. Did anybody get that? If you did, say, uh-huh.
That's what I got.
Yay. Now we can look that up in the back, in the answer book, the 735, and it says, at the bottom, the spacing is 1.36. Well, that's the same thing we got. The book got 1.36 inches between nails. They just rounded off is all. Any comments or questions on that? Well, okay, you got some homework for me. And we studied shear flow today. What it's useful for is when they build these members up, when they maybe glue a bunch of boards together or nail them together. And see, there's a problem. They want to slide with one another. It's called shear flow. We have an equation for it. Any comments or questions? Yeah, I think you have a test next Tuesday. It'll be available.
Mr. Griffin, I have a question.
Yeah, go ahead.
What is the 1.69 inches on your board there? What does that mean? What does that go to?
Thanks for asking. Now who am I talking to?
Oh, this is Brian Davis.
Brian. Thanks, Brian. I'm trying to find a 1.69. Where's this 1.69?
Bottom right.
Bottom right.
Yep.
Oh, yeah,
Right.
1.69. Gosh, Brian, I don't know. Does anybody out there know what? I don't know what it is. Brian, erase it. I think maybe it was a mistake. Remember, I did it wrong the first time. Thank you for asking, though. But I think we got it right. We got two different answers. We got a 1.14 and a 1.358, and those are correct. Thanks for asking, Brian. I honestly don't know what it was. Watch the YouTube video, Brian. It'll tell you. Anybody else? Well, okay, I'm going to push this red button unless you say something. 5, 4, 3, 2, 1. Bye-bye, students.
Bye, Mr. Griffin.
Bye,
Bye-bye.
Professor.
See you next time. All right. Adios, muchachos.